Problem 8. A 1 microfarad capacitor is connected to a 24-volt battery. How much energy is stored in a capacitor? This is why you should discharge capacitors before you touch them. Alright, so this is a pretty easy problem. You can just look at the formula, throw in the numbers, and get it. But there's actually a lot of information packed in here, which is probably worth discussing. Alright, so not too big into derivations in life, but this one's kind of worthwhile. So we know that volts are potential energy. Potential energy. So potential energy, joules, is voltage times charge Q. And so if we want a small amount of U, I'll say delta U, and for a voltage, we'd have a delta Q. So delta U equals voltage times delta Q. Okay? Integrate both sides. Hop, hop. We get integral of V dq, where for a capacitor, we know that capacitance equals Q over V. Therefore, V equals Q over C. So we have the integral of Q, that's supposed to be a C right there, over C dq. Okay? So we take the integral of Q with respect to Q, and we get Q squared over C, 2C. Okay? And that is the amount of energy we have in a capacitor. So that formula is not actually as useful, so I'm going to rewrite that using the same capacitance relationship as Q equals CV. So then Q squared equals C squared V squared. So I have C squared V squared over 2C, which equals, cancel out one of these guys, 1/2 CV squared. I like this equation better because it's easier to memorize. It's also usually more useful too. So I like to think of this as the kinetic energy equation. That creates gross conceptual errors because this is V is for voltage, the other one is for velocity. That's okay, doesn't matter, helps you remember it. So if you think of this C as mass, it defines how much, it defines the relationship between charge and voltage of a capacitor. So it's kind of like, mass, kind of, same idea maybe, I don't know. And then V is voltage. So that is the equation. And so then we take 24 volts, 1 microfarad, and we have 1 microfarad, 1 times 10 to the negative 6th. I'm just going to pretend that dot isn't there. Over 2, it's a microfarad, times 24 volts squared. Is it 24 volts? A 24 volt battery? Yes. Yes, it is. Okay, so then we're going to do 1 times 10 to the negative 6 times 24 squared divided by 2. We have, that's pretty small. 1, 2, 3. How small is that? 1, 2, 3, 4, 5, 6. I'm going to say 288 microjoules. Okay, 288. That's a terrible 8. See if I can do better. And slightly better, but not much. Had the capacitor been connected to a 6-volt battery, how much energy would be stored? That's really not challenging us. So I'm going to change the 24 to a 6. Man. All right. 1, 2, 3, 4, 5, 18. 18. And they probably want to see something about the relation of the ratio squared. But I don't care. All right. So one other thing to look at here is Earlier, before I mentioned the hydraulic analogy, I'm a big believer in the hydraulic analogy. If we drew this in a picture, okay, it would look like this. There's the battery, and here's the capacitor. So the hydraulic analogy, the way this would relate, if you haven't looked it up, I would highly recommend it. Go to Wikipedia, hydraulic analogy, and read it. This basically, hydraulic analogy really pays dividends when you start talking about components. When you stop thinking of things in terms of energy and in terms of energy and force, you start thinking of it as just components and pieces and formulas. All right. So the way you think of this intuitively is pressure and pressure. So a battery is represented by a pump. Here's a pump. That's supposed to be a pipe. I'll make it, there we go. Pipe. And then there's a diaphragm, which is what a capacitor is. So what happens is, and then this will be a pipe too. So what happens is pump starts, it pushes pressure this way, and it stretches the diaphragm. So that stretching of the diaphragm is what's storing the energy. The stretching of the rubber is storing energy. So it pushes the diaphragm over a little bit, it stays there, and you have all this energy built up. It's the same idea with the capacitor. This is pushing electrons to this side. Actually, it's the way the battery convention is, it's pushing electrons to the other side. So it's pushing positive charges over here. Really, it's pushing negative charges to the other side, but that's, by convention, a battery pushes positive charges. So for current, the direction of current is the direction of positive charges flowing. So what it does is, just like it pushes more water on this side, less water on this side, the battery pushes more positive charges on this side and more negative charges on that side. And that's how a capacitor is represented in the hydraulic analogy. All right? Sounds good. On to number 9.